The mic was muted all along. Don't worry. So, right equilibria, first hydrolysis M3 plus H2O, MOH twice, 2 plus H plus Ka1, second hydrolysis MOH2 plus H2O, MOH2. So these are first form of hydrolysis. Okay. Is there any pattern I could follow to predict this K? I don't know. Two reactions. Shazim Khan, hi. Hey, yo, what's up? What's good? I'm guessing it's just your first time here, right? Yeah, I never seen your name before. Shazib Khan. What's good, gang? I don't know how to go with do. Or is this the Yes, there's a clear pattern. You're not supposed to invent these reactions randomly. Hydrolysis of metal cations follow a very symmetric subwise pattern. The metal cation in water exists as hydrated complexes first. Okay. I'm not doing anything. What? You fucking kidding me, ChatGPT? This shit's hilarious. Hilarious. Has your set a time for 30 minutes? Sir S block in short bataille, please. Oh shit, you're the first one who asked me a question. Okay. S block. Oh, what was S block though? S block is when the god damn it. It's when the valence electrons are the outermost electron shell, the valence electron in the outermost shell is contained in the S block or S subshell, the spherical one. That would be the S block from my understanding. Every element in the S block is having the outermost electron shell being part of S subshell. Does that make sense, bro? I appreciate that. I appreciate the random testing of my knowledge. The same goes for P block, D block, F block, and imaginary G block. Z outermost shell. Oh shit. Okay, I got a new one. During DD transition, why the d orbital split into two suborbitals? Not gonna lie, I don't know. What is the DD transition? That's the first time I'm hearing that. Copy. DD transition. Interesting. Let's look it up. Oh, ChatGPT is just fucking. DD transition is excitation of an electron from a lower energy d orbital to a high energy d orbital within a transition metal complex, typically caused by the absorption of visible light. This transition occurs in metal ions with partially filled d orbitals who are responsible for the vibrant colors of many coordination compounds. Okay. The degenerate d orbitals split into different energy levels. In octahedral complexes, an electron absorbs energy to move between these two split levels. Okay, I did not know that. Are you a sort of chemistry major, Shazib Khan? That's some elite ball knowledge. DD transition. What is? I'm gonna close GPT. DD. So I still didn't understand the split part. That was pretty. Mm-hmm. Dude, it's all long videos. Crystal field excitation is an electronic transition of an electron between two orbitals of an atom that is situated in a crystal field environment. It's the electronic transition of an electron between. What? Electronic transfer of an electron between two orbitals of an atom, of the same atom. Two orbitals. Is it lower? I'm guessing from lower orbital to higher one. That is situated in a crystal field environment. They are often observed in coordination complexes of transition metals. Some examples of crystal field excitation are DD transition on a copper atom that is surrounded by an octahedron of oxygen atom, or FF transition on uranium atom. Mm-hmm. From one D to another D orbital. So I'm guessing both. It's like what's the numbers though? Magnetic quantum number, right? That's the one that decides which subshell are we talking about. If I understand So one d orbital. So one d orbital of a specific magnetic quantum number. D orbital is gonna be having right like 3, 4, B 4. So for nine suborbitals. It works on the principle of quantization of energy. The energy needed for the ground state electrons to jump into the next. I'm still not getting the. I'm still not. I still don't know if I understand this. How does it happen when splitting up the general orbit takes place in ligands? The electrons in the tag absorbs the required energy and jump from the lower energy orbital. How does the same orbital have two different energy levels? I thought it was all equal distribution. Principle of DD transition. It works on the principle of quantization of energy. The energy needed. Stupid. This fucking app so stupid. Shazib Khan, did you just leave with elite ball knowledge? Who's gonna know? Occurs in transition metal complexes when electrons absorb specific visible light wavelength to jump between split d orbitals. What's with the split d orbitals? The orbital is a division of phi d generate equal amount, again, equal energy. Transition metals into two more distinct energy levels due to the repulsive interaction with the surrounding ligands. Ah. So, due to ligands, the the magnetic quantum number, different subshells, how do I say, the or energy levels within the d orbital have different energy levels within itself. Two or more distinct energy levels due to the repulsive interaction with surrounding ligands. Repulsive interaction with surrounding ligands. How does the ligands result in distinct energy levels for a subshell? That's like a part of the atom, right? Why does something external control that? This phenomena splits orbitals into higher and lower energy sets. I gotta ask GPT on this. This shit's fucking. It's my first time I'm hearing about that. Pattern can memorize. MNZ plus. Oh, okay. This is the one. Ah. How many Ka values exist? For M3 plus, there are up to 3 hydrolysis step. General rule: if a metal charge Z equals maximum steps possible. Oh, okay, okay. I did not know that. So this will go on until Z minus 0. Just a minute. What's up? I accidentally got the important call and I had to mute my screen. Guest 1337I. Hey, yo, what's up? I apologize, gang. I apologize. Copy. Where's Discord? I'm gonna paste it onto Discord. How long was I not here? 30 minutes? The stream is going on for 1 hour 23, okay? Okay. Bam, 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 bam. Ba 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 bam 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 ba 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 bam 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 ba 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 bam 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 bam. I haven't made any shorts. I don't feel good. But right now, let's focus on inorganic chemistry. This exactly, it continues if the charge is reduced to zero. If you start with M2 plus, Z plus, Z plus n species. So, okay, can you show me the equation for 3 type of metals with n equals 1, 2, 3? But yeah. Let's write it cleanly for trivalent metals. We'll show the stepwise hydrolysis reaction for n equals 1, 2, 3, starting species in water. In reality, it exists as an aqua complex. We'll use the simplified notation like in your notes. No, what are you even saying, bro? I'm talking about this one. I'm talking something like this, or could you show me the Ka1 high acidity classification for moderately acidic cations. Cations? Yeah, cations. Reaction with salts with water may be exothermic, can be dangerous. pK6, strongly acidic cations. Okay. Okay. Now we will write the actual hydrolysis steps for real metals. I'll write them in a simplified form. Your notes use aluminium. Aluminium? No, aluminium. Right? Yep. AL3 plus 3 steps, K1, K2, K3. Final species, ALOH thrice. Yes, 1337I. Yo, what's up? It was the screen was black because I was attending an important call. A really important call. That's why. 84. 10 minutes, okay. Laptop is 100%. You know what? Why won't you show this? Why won't you show this, gang? Okay, the equations looks blank. Stop. Latex text. I switched at a time for 30 minutes. Why is it so slow right now? Is it because a lot of tabs open? Whisper, oh, I haven't used Whisper, but it's still there. Guess 1337 or YouTube thing or YouTube name. How's it going? I gotta say, I think I didn't tell you, right? The interview went pretty good. You know how it should be, right? They just saw me and like, oh, is this guy? Oh, okay, okay. Al3 plus to H2O, AlOH twice plus 2 or 2 AlOH2 plus H2O. Okay, what? Second species is one OH atom. Okay, looks like you can show me the equations at least. At least it's not in understandable form. What should I search in Google to get this equation? Okay, that's no, that's not what I wanted. Can I download it though? I gotta log in. Mm. Wait, that's photic salts. No, no, this is not what I meant. It's just different metals, right? You're right. That search phrase is too general and will mostly pull up random lecture slides or unhelpful notes. You want something too much more specific so that the actual stepwise hydrolysis reactions show up with clean formatting. Here are the best search phrases that will give you properly formatted stepwise equation. Okay. I don't know if I could get that. Ale, so that's 3 plus from ale, right? Then we got 2 plus, then plus, and that's like the. Uh huh. What was the general formula though? Oh, now you want to show no. What the fuck? Whoa, 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 whoa. I'ma join the subreddit though. I'm getting distracted again. Where's the general equation? Yep. So it was Z. That's the general equation. So is that same? Is where do we got the H plus? We got H3. Oh, that's good. Why do we start with this though? Oh, it's either Al3 plus or AlH2O. It's like the ligands, right? Yep. If I understand, these are the ligands. I should write these. %91. That would be enough, right? Oh. What? It's still 5%? What was charging then? It's not even charging? Yo. Okay, I'll put that on my notes though. Okay. That's not looking good. So I had a question before. Where is the question I was doing? What was that? Good. Let's redo it cleanly structured. So M3 plus. We got the K1 and K2. This should have 4 steps, right? Or 3 steps. How many steps exactly? For it's not a readable form, but okay. Z minus 1 Three steps. Okay. What is KW? Water's autoionization. We want H2O plus and pH. Write the equilibria. Yeah. Start with the dominant step, Ka1. Ka1 is 10 raised to minus 3. Yeah. 10 raised to minus 6. Ka1 is 1000 times larger. First step dominates acidity. Okay. That makes sense. Solve first hydrolysis properly. X equals from first step, ice table first step only. Minus x plus x plus x. What? The x value decreasing and increasing. Can you show me what exactly is losing and gaining and let's break the ice table step by step. Species M3 plus 0.1, change in M. Initial M minus X. So yeah, MOH2 plus, the oxide form. Okay. So it splits water. Okay. So that much H plus is going to be released. Equilibrium. With water to form and releasing but I'm just wondering, in this case, 1H2O is being absorbed by the metal and releasing H plus. So what's the case for metals that absorb two OH minus or 3 OH minus? Also, how do I know if the said metal is absorbing 1, 2, or 3, etc. Or this is also related to the pKa, and higher pKa's are less likely and usually is gonna be, or mostly is gonna be, single metal ion absorbing single OH minus. What hydrolysis reaction really is? The generic first hydrolysis step is here one water molecule donates OH minus to the metal ion. The metal ion loses one positive charge. The proton H plus is released into solution. So absorbing one H is standard for each step. When metals absorb more than one more OH minus, each subsequent adds more OH minus to the metal. So it's always one OH minus per step, even if the metal ends up binding 2 or 3. So how do we know how many steps there we go? It depends on the metal's charge. Okay, reason the metal can stabilize the extra OH minus until its all positive charge is neutralized. Okay. So the metal first absorbs an OH minus, and if it has more positive charge, it's gonna absorb other OH minuses. Okay, that's understandable. But how is the H plus gonna be affected? Relation to Ka and pKa. The first hydrolysis usually the largest, easiest, high charge, stronger acid, bigger Ka. One second hydrolysis Ka2 smaller because now the metal already has an OH minus attached, less acidic. Third and fourth even smaller Ka step less likely to occur. Rule of thumb: higher metal charge, more steps possible. Stronger hydrolysis overall. Low charge, maybe only one step occurs. Okay, I understand that the more charge they have, more OH minus is absorbed. So more OH minus absorbed means more H plus and thus acidity. But how do we know? The first hydrolysis is what happens for wait. K expression K1 equals X times X. Okay, now when you explained the Ka, could you remind the equation for Ka? I mean, do I need that? X minus X. So Mn3 MnOH2 plus. So it's product by reactant, right? Yep. I don't need to know that. Product by reactant. Megumi from Undertale. When are you gonna play Undertale? Interesting question. So I could play Undertale if there's an engaging viewer. That's like the whole point. You know what I'm saying? So Megumi from Undertale. If you're gonna stick here for a while, or if you're gonna engage, we could play Undertale for a bit. I'm guessing you completed the game, right? Of course. Making me from Undertale, did you just vanish? So, okay, is equal to 10 raised to 3 with this equation. Okay. Use weak acid approximation. Assume 0.01. Okay, so if x is really small, because it's a weak acid, then. But M3 plus, that sounds like a strong acid, right? X equals here from what the weak acid approximation is only valid when the metal acid ion is having lower charge, but here it's +3, so I'm guessing it should be what? What makes it can undergo the weak acid approximation? Is it the metal ion? The weak acid approximation assumes only a small fraction of the initial acid dissociates mathematically. Strongly polarizing, so it can be strongly acidic, but the dissociation also depends on the concentration of the metal. Ka alone does not determine if the approximation is valid. If Ka times C, that matters. If your example, Ka is equal to C equals 4.01, X so concentration times the constant, equilibrium constant. So the 30% dissociation is borderline. Okay. I'll do it later. 30 minutes? Okay. That's a good break. Let me go get a coffee and 10 minutes of beatbox. I want to try beatbox. Not beatbox, beatbox. Where's the 50 cents though? Is it in here? Where my 50 cents at? There we go. There we go. Hey Siri, set a timer for 10 minutes. 10 minutes, counting down. Where's my beatbox? Ahahaha. Takio drum. Gunshot, reverse cymbal, metal pipe. Metal pipe. Oh. Wait, can I change this midway? So if I play it. Okay, so I cannot. It's either I have to custom instruments. Reverb. Okay. No, I don't want to do that. Cancel. Can we not do that though? Woodblock standard drum set. Okay. Yeah. Just a minute. Just a minute, gang. I had to stop again. I know. This shit's not looking good. back in the game. Back. So we're trying boom beatbox. Oh. Uh-huh. Oh, that's too powerful. Nah. It is pretty fun. Why is it sawtooth right now? Mm-hmm. Ukulele. Violin. Bagpipe. Mouse. Echo drop. Gumdrop. What is gumdrop? Alto sax. Cola. So we got 333. Oh, it still goes. Okay, okay. I forgot. Wait, what? Oh, that was 6. Okay, we got 6. Okay, okay. This shit's fun. This shit's fun, not gonna lie. Okay, I gotta stop. I gotta continue with the Organic Chemistry. Hey Siri, set a timer for 30 minutes. Recharge headset. Exactly, you're spotting the subtle XSH plus formed in your example. Ka is 10 raised to minus 3. Concentration is really low, so root of. But also, I remember doing that this formula is only specific to one part, right? Like, there are different formula for different cases. Exactly, that formula is non-universal. It works under specific conditions. Let's break it down clearly. Formula x equals root of kc derived from x squared by ka equals x squared by c minus x. Approximation conditions for using this. Acid must be very weak enough for that fraction, enough that the fraction dissociation is small. Single dissociation only weak acid. If fraction dissociated is 5 to 10%, use quadratic formula. For multiple hydrolysis steps or strong acid, do stepwise calculation or exact solution. Can I get the prob question that involves these three? I mean, three cases with uh, strong acid, moderate acid, and weak acid. Further reactions. To return to previously discussed reaction, still has a charge on the product. Okay. So this is where, yeah, 4 plus 3 plus 2 plus 1 plus, yeah, general formula. Further products, hydrated hydroxide isn't very stable, so it forms abbreviated reactions. Titanium dioxide is an important white pigment example used in toothpaste, sunscreen, paint, etc. Gaseous HCl forms dangerous. So where is so it's formed on TiCl4. Did we start with TiCl4? Oh yeah. Calculating pKa. pKa equals example math. Most plus 1 blocks equation including En pKa, if x of p greater than 1.8, move up one acidity category calculated with z squared by r. Simple sample calculation. What r must a 5 plus cation have to exist in water? Very strongly acidic cation do not exist in water. For very strongly acidic pKa to come out of the equation, for a species to exist in water. Sample question. Classify the cations and describe reaction with water. EU2 plus B3 plus. Oh, we're still here. W6 plus. Classify cations and describe reaction in water. So W6 plus is gonna react a lot. Need XPZ squared by R form tables. EU2 plus R 1.31 picometer radius. Estimate XP using neighboring elements and trends. Sample question concentration. Oh, it's the same. Okay. So T3 plus radius is 41 picometers. How do you know the radius though? It's very strongly acidic. Sample question concentration. Reaction with water. EuCl2 feebly acidic, dissociates but basically zero reaction. Equilibrium on left, low H3O plus concentration. Okay, we got EU2 plus, right? Very strongly acidic, reacts completely, makes high product, but also a lot of heat, dangerous. So again, what makes us decide if the metal is highly acidic or not? Is it the 2 plus 3 plus charge? Amount of number of ligands attached to the metal? Is that what makes us decide? I'm guessing that's what makes us decide. I'll do the sample question from here, right? You're given three aqueous solutions, HCl 0.05. I think that's, where is it? Not this one. Yeah, sample question, this one. I think this one helps. Hydration. Metal cations are hydrated in water, denoted with the aqueous dissociation. Hydration, exothermic process, high Z, small r, more heat. Latiman equation C right. Equation C right, okay. Radius of the cation plus 50. Mm-hmm. Driven by Coulomb attraction charge on ion, non-polarity on H2O molecule. Fc proportional to Z plus cross Z by D square, where Z plus is the charge, M plus Z minus is the negative. Okay, on O and D is the distance between the two. Cation radius 30 picometers. Wait. Again, why are we focusing on radius, and does the question give us radius every time? Or do we have to figure it out from the periodic table? From the periodic table? Is that how you do it? I keep on giving in the address, but it's not working. Wait. Where's the There we go. Can we go a little bit? No. You are given 3 aqueous solutions: HCl, 0.05 strong acid, acetic acid, moderate acid, metal cation, weak acid approximation, borderline. Calculate H plus and pH of each solution. Indicate which formula or approximation you used in each case and why. HCl, strong acid, fully dissociated. H plus 0. pH minus log of 1.3. Acetic acid, Ka time multiplied by C equals 1.18. That's Ka. Okay, so Ka is moderate acid. Do we use this one? We use fraction dissociation. And the last one, okay. It's very small. Weak acid approximation is actually okay here. So it should be more than 5 to 10%. This value should be more than 5 to 10%, 15% to use the dissociation. What should I factor here for using which formula, like let's assume I don't know which is strong acid and weak. You're touching the key decision maker. Stop. Fraction dissociation, deciding factor fraction dissociation is H plus by acid, the concentration of acid initial. So if F is greater than or very less than 5%, dissociation is very small, weak acid approximation works. If greater than 10 to 15%, weak acid approximation is not valid, must solve quadratic. Okay, so you cannot just the x z minus x should be used. If F is 100%, essentially fully dissociation strong acid, H plus is equal to the concentration of C. Oh, fully dissociation, that means the initial concentration of the acid or metal is the final concentration of H plus produced, which is literally translating to pH. Step by step without knowing acid strengths. If you don't know whether it's a strong or acid, weak acid, assume weak acid first, calculate fraction dissociation, check validity of, okay, strong acid. Let's try solving this one. But what I have noticed is the use of radius is mentioned here. What's up with that? Why radius matter? When a cation dissolves in water, it pulls on the electron cloud of water molecules. The smaller the radius, higher the charge. So why are we using z squared by r as a rough measure of charge density? Charge density equals z squared by r. Why electronegativity is used for some cation, the polarizability / tendency to pull electron is affected by the electronegativity of the metal. For EU is unknown, but we estimate for neighboring lanthanides. So why is this question approached with the radius and electronegativity compared to the one like what's the fraction dissociation? Approach for metal ion acidity. So it's only for metal ion. Approach. This is predictive / qualitative. You don't know Ka yet. You only know the cation's properties: charge, size, electronegativity. Goal: classify the cation as feebly, moderately, or strongly acidic before doing any calculation. Useful for new cations or when no experimental Ka is given. Works based on physical / electrostatics. Small, highly charged cations, strong polarization of water, strong acidity. Example, EU2 plus gives Z2 by R 0.031, feebly acidic, barely hydrolyzes in water. Okay. Let me wash my hands. So, hmm, hmm. Fractional dissociation, I stay. Oh, don't get distracted. Known info only: cation properties, Ka and initial concentration C. Classify acidity quantitatively, compute pH quantitatively, electrostatics and periodic terms, equilibrium calculation. So, so again, are these two approaches part of inorganic, or the radius electronegativity more towards they both are exactly approaches purely in organic chemistry. It's all about properties of metal cations, their charge, size, and strengths in periodic table, which are classic in organic concepts. This is what you see in the metal ion hydrolysis, cation acidity, and transition slash lanthanide chemistry. You're predicting behavior from periodic trends, not solving solutions equilibria yet. The fraction dissociation pH calculated come from analytical chemistry, general chemistry. It's more quantitative, more. Okay, this part. Okay. So produce oxides in water, further products, abbreviated reactions. Titanium dioxide is a important white pigment example used in toothpaste, sunscreen. Okay, calculating pKa. Relationship between cationic Z ratios and acidities. Zoom. Most +1 S block ions, non-acidic ratio, feebly acidic. Feebly acidic, that's even examples. Yes, this section is basically giving you a quantitative way to estimate the acidity of a metal cation based on inorganic properties instead of relying on experimental Ka. What factors affect the metal cation acidity? Charge, higher charge, strong attraction of water, strong polarization, cation radius, smaller radius, stronger charge density, stronger polarization, electronegativity, higher electronegativity. Cation can attract electrons more. Cation can attract electrons more strongly, enhances acidity. Okay, so the formula: low ion cations. Low electronegativity cations, less than 1.5. Z in unit elements charge, Z squared by R. Term adjusts for electronegativity, making the cation more acidic if XP is greater than, or the electronegativity is greater than 1.5. What R must a 5 plus cation have to exist in water? Very strong acidic cations do not exist in water. 0.22 less than or equal to Z squared for very strongly acidic pK to come out of the equation. So the Z square is 5 plus, right? So 25 by R. So it should be greater than 144 picometers, or less than 144 picometers. Okay. Again, if it's less than 144 picometers, only then it can show its acidic properties and dissociate in water. Okay, so we got a high number of charges. Z is pretty high here. High electronegativity cations, pK equals 15.14. Where did you get these numbers, dog? Where did you get the 15.14 value? Like the 15.14 and I also got a table with the relationships between cationic Z plus by R ratios and acidities. So first one on the table was most +1 S block ion non-acidic under category En less than 1.8. Then Z squared divided by R, it was from 0.00 to 0.01. Then category if en is the greater than 1.6, feebly acidic. I don't know this term. Does that mean weak acid or something even lower? TL plus. Could you explain what this table is about? Now you're getting to the classic inorganic cation acidity chart, which is essentially a shortcut for predicting how an acidic cation is in water. Let me break down what your table is showing. The basic idea: metal cations in water can act as acids by polarizing water and releasing H plus. Mz plus plus H2O equals MOH Z minus 1 plus H plus. How acidic they are dependent on mainly on charge. Yeah. How the table works. Most plus 1 S block ions. Group plus 1 ions. Usually non-acidic. Electronegativity 30 minutes. Okay. Electronegativity less than 1.8. Only consider Z squared by R ratio. Low electronegativity, usually weakly acidic or non-acidic. Z squared by R charge density is suitable. Units usually E squared by picometers. Category acidity is adjust acidity if the cation is more electronegativity negative than threshold. Examples: real ions that fit in this category is TO is a feebly acidic, feebly very weak acid cation, barely hydrolyzes water. Okay, that's feebly. So it's even weaker than what's it called? Weak acids. That's a whole lot of stuff. $30. I'm gonna take a 10-minute break of beatbox. Okay, so set a timer for 10 minutes. Oh, whoa. Whelp or Wlep. Guest 1337. Wlep. What do you mean by that? Oh, a lot of stuff. Is there a way I can get rid of it altogether? Nope. I have to press individually. No, I don't want to press individually. Okay, what do we have here? Nothing. Eight. Oh, there's no eight. There's seven. Yeah, there's eight. Oh, what is this one? Ah, what is that? Stop. Hmm. I still haven't found the one I was looking for. Oh no. Oh no. No, here. So nothing, right? On a clean slate. Metallic pad, bowed glass, new age pad. Oh. Steel pan. Telephone ring, buzz saw, scoot, dark strike. Oh. Oh, that's good. Mm-hmm. Now every what? Uh, what do I add though? It's too loud. Squire wave. Pulse width. Oh. Yeah, yeah. Okay. Nah. Brightness, sci-fi, steel pan, metallic. Bird tweet. Nah. Telephone. I did brightness. Synth kick. Oh, we got tiny robot. $10? Okay. Okay. Well, that's 10 minutes. I gotta say, it's fun. It's really fun to look at this. So, where? Basic idea: metal cation in water can act as acids by polarizing water and releasing H plus. So most plus one block elements, again terms: feebly acidic, moderately acidic. Think of it as a quantitative ranking. So most plus 3 D block ions, most plus 4 D block ions, very strongly acidic, most P block cations. Quick qualitative: is this cation feebly, moderately, strongly acidic? Equation: quantitative calculates approximate pK from ZRXP. Wait, what? Wait, what? Wait, what? Okay. I'm starting to get something, but another one doubt I had was like, I know how the radius trend is across the PT and the EN across the PT, but I don't know the specific picometers, etc. So how do I solve such a question if I get it? Or this is the solution to that by following table, you get the ratio you're looking for. Why you don't need exact picometers or electronegativity values. The exam question, they rarely expect you to know every cation radius in picometer. The table gives you a range. Okay. Why is there a second 10 minutes timer? I don't know. Hey Siri, set a timer for 30 minutes. So can you give me the table? I just let me see if is similar to I can make a compact table of cation acidity using z squared by r ratios, electronegativity, and general trends, so you can compare it to your notes. I'll organize it by block of periodic table. It also indicates the acidity category: feebly, moderately acidic, strongly acidic. This block. Oh, is it true though? S block +1 alkali metals, non-acidic, feebly less than 1.8. Okay, it's 0.202 to 0.04. Moderately acidic, so 0.4 to 0.10. No, there's slight number variations. Most +4. There's the difference. Let me see how the rest are. Let me just see before I stop this to stop the stream for now. I need to cook something. Coordination. Maximum coordination number helps predict reactivity, predict based on chemical properties, predict based on physical properties, maximum number of atoms that can bind to the central atom. TiCl4, strongly acidic, violently reacts with water. CCl4, very strongly acidic, no reaction in water. Steric effects, small C atoms surrounded by 4 large Cl atoms. H2O cannot get a C at start to start reaction. MCN depends on the size, which depends on the period. MCN increases down. Period 2, MCN4, octet rule. Period 3, 4, MCN6. MCN sample questions: will SF6 react with water? Strongly acidic in theory, complete reaction with water. Check MCN. Period 3, MCN6 already has 6 F ligands. MCN reached no reaction with water. MCN sample question 2. Will TEF6 react with water? I don't know. ARL from somewhere. Yo, what's up? Hey, yo, what's up? How you doing? Appreciate you for checking out the stream. And yep, I was just checking out Inorganic Chemistry, and I gotta say, there's a lot to read. But if I could read everything, or if I could learn everything within the amount of time, within the time limit I got, I kind of broke it. I kind of did it. But before that, let me check one more thing. Mega file. How is studies going, ARL, from somewhere? Second semester, god damn it. Chemical thermodynamics, analytical lab, general lab. Oh, lab course. Oh. So what are the things we do? How many pages is there? 47 pages, okay. Arrangement of lab course. Separation of section 1, section 2, section 3, section 4, section... There's 7 sections, okay. Section 1, separation of ternary mixture. So... So we got 7 experiments for lab. 6, no, not 7, 6. Section 6. Where did I see section 7 then? Oh, section 4 and section 5 are together? Why though? Why though? Preparative synthesis, that's section 7. Where's section 7 though? There's no preparative. So that's the notes. What else? Group assessment. These are older. There's a lab exam. There are some stuff to do. Okay. Okay. 44 pages of protocol? Really? Section 6. Section 7. Oh, okay. Wow. Oh, okay, that's the... Okay. Correction protocol section 2. Okay. How's the analytical lab looking? Okay, guys. I'm gonna end the stream. I gotta cook something real fast, and after cooking, I'll be back. That should be something that's gonna happen, and I'm not gonna take a step back. I'll be back. Peace out, YouTube.